Let me start with two observations. Observation one, machine learning is making a lot of progress in the recent decade, but despite that, 95% of the research in machine learning is on the following single problem. How do we estimate a function given input-output examples of that function? That's observation one. Observation two is when I tell my mom what I do for a living, she's not that impressed. Because I tell her I work on machine learning. She says, okay, what's that? And I tell her it's getting computers to learn from experience. She's happy so far. She says, give me an example. I said, well, like, credit card transactions, are they fraudulent or not? We get some historical, and then her eyes start to glaze over. And the reason she's not that impressed is she watched me grow up. She knows what learning means. She helped me learn. She watched me learn. And she knows that what learning means is that when I was very small, first I had to learn to crawl, then I could learn to walk, then I could learn to ride a bike, maybe play tennis. In parallel with that, I learned to say words, I learned to speak, I learned to do other things. Somewhere along the line, I learned to count, I learned arithmetic, I learned algebra, I learned calculus, and some other track was learning physics. And I was getting synergy between all these things, and I learned them in a particular sequence, right? It would not have made a lot of sense to start with algebra and later do counting. And she knows what learning means. So that's the sense in which she's not that impressed, because she thinks, well, you call it machine learning, but learning is really this stuff. So that's really partly the motivation for this work, is that it's time for us to get serious about what our moms think we're doing and try to address the question of what would it take to raise a computer? What would it take to build a computer that learns, that's a persistent software individual, that learns many functions over a long period of time, that gets synergy among those, that learns the easier things first and then the harder things, and that has the property like you do, that the more you learn, the better learner you become. Right after you learn to count, then you can learn algebra, but not before. So there's some positive feedback there in when you acquire some knowledge, it opens the door to make you capable of learning some other kind of knowledge. So the question I want you all to help me think about for the next 45 minutes is, what would it take to have computer programs that behave this way? And I want to ground the discussion with a case study. We've been working on a system we call our never-ending language learner, NELL, which has the following specification. Here's what we're trying to do. I want to build a system that essentially learns to read the web. That's a ambitious enough task that it won't be solved any time in the next week or two. So it has plenty of, it's complicated enough that it could make a case study for a never-ending learner. And the inputs that we're going to give NELL, that we have given NELL, are an initial ontology that defines categories and relations of interest that we want it to read about. We've given it roughly 600 or 800 predicates, categories and relations, like person. We're interested in the category of people, and also athletes, which are a subset of people, and also companies, and also emotions, and also foods, and also relations among those. Two-place predicates like which person works in which company, or which food goes with, which food is liked by which person, things like that. So given an ontology, and for each of those predicates, roughly a dozen examples. If we're interested in universities as a category, then we'll give examples, a dozen of them, Purdue, CMU, etc. The web, that's unlabeled data, and occasional interaction with humans, which is turning out to be about 5 minutes a day because we're all busy. And then given those inputs, here's the task. It's very easy to state. We just want a system that runs forever. And each day does just these two things. It has to extract more facts or beliefs from the unstructured text that's on the web. And just as important, maybe more important, number two, it has to learn to do task number one better each day. Right? So we want it to learn to read better each day. What would be the evidence for that? Well, if we sent the system back to the same text that it looked at yesterday, if we send it back to that same text today, if it has learned to read better, it should be able to acquire more facts more accurately from that same text. That's what it means to learn, right? Okay, so that's the problem. We have not fully solved it, but we have a system that has been running now for over 2.5 years. It started in January 2010. You're all invited to the birthday party, big birthday party, 3-year-old coming up next January. And so far, it has acquired a knowledge base with well over 15 million candidate beliefs, and a couple million of those in which it has high confidence, and whose accuracy in the 2 million that it's most confident in, it's about 80 to 85% accurate. So still not reading perfectly, but it's acquiring an interestingly large collection of beliefs. It's learning to read better each day. It's a better reader now than it was last month. It was better last month than it was last year. And it's now beginning also to learn to reason, to infer new beliefs, not just by reading, but also by inferring them from other beliefs it has. And it's now beginning to also extend the ontology. We initially gave it our own ideas about what would be interesting categories and relations to read about. Now it's making up new categories and new relations. So that's what NELL is. And what I want to do is sort of lay out what it does and then leave plenty of time at the end for a discussion about this and the whole research topic. So when I say that it has a knowledge base with millions of facts or beliefs, I'll call them beliefs because they're not all correct. Here's a snippet of that. So each of these red arrows represents some triple, like the Maple Leafs' hometown is Toronto. That's one of the beliefs, one of the millions of beliefs NELL has. And there's a confidence it has associated with each of these that I didn't show here. It believes Toronto has a city stadium called Air Canada Centre. It believes the Maple Leafs won the Stanley Cup, which the Red Wings also won, who are in Detroit, which have a company called General Motors that competes with Toyota that acquired Hino. So you get the idea. It's a fairly diverse set of beliefs. And this is its growing knowledge base. You can go to this URL and browse the knowledge base yourself. In fact, you can download it if you have any interest in doing that. And if you go there, you'll see some random sample of recently extracted beliefs. And you can drill down on any of them. In fact, I want to show you T as an example to show more about what's inside NELL. Ask me later. Okay, so one thing that NELL has to do, right, its job is to populate this knowledge base. So one key part of that is to look around the web for noun phrases. And for each noun phrase, it has about 50 million noun phrases that occur fairly frequently on the web. For every single one of those noun phrases, NELL wants to figure out what's the type of entity that this noun phrase refers to. So let's take a look at T, for example. And T, NELL believes, is a noun phrase that refers to an agricultural product. It also believes T is a noun phrase that refers to a food, and it believes T is a noun phrase that refers to a beverage. And why does it believe this? So here's the key idea number one. It believes that T refers to a beverage because it found the noun phrase T in the context large cup of tea. And it also found it in the context afternoon cup of tea, and drinks other than tea, and complimentary cup of tea, and cappuccino, comma, hot tea, and lunch, comma, high tea, and ultimate cup of tea, and so forth. And every one of those mentions that it found of the noun phrase tea that occurred in these contexts gave it a little bit of probabilistic evidence that tea is probably a noun phrase that refers to a beverage. And you'd have to agree with me that any noun phrase that occurs in all these contexts probably is a beverage. Okay, now, of course, the question is, how did NELL know to use these contexts as opposed to some other phrases to determine T? And the answer is that's what it's been learning for the last 2.5 years. So NELL now has tens of thousands, probably hundreds of thousands, of different phrasings that it uses as one of its methods for extracting information from unstructured text. You can see here it has a lot of different phrases that it has used, really kind of overwhelming evidence that T is a noun phrase that refers to a beverage. Okay, so idea number one, NELL doesn't read like you and I. We take a sentence and we really understand every single word in that sentence. NELL takes the web, actually 500 million pages that were downloaded from the web, thanks to Jamie Callan, and it does a shallow analysis of every mention it can find of the noun phrase T. And each one of those mentions might give it a little bit of probabilistic evidence about that noun phrase. Taken together, it gets very strong evidence for supporting this particular belief. Okay, so let's see what else NELL believes about T. It also believes that T participates in some relations. It believes that tea is an agricultural product that came from the country Japan and Kenya and South Vietnam. It believes that it's an agricultural product that contains the chemical antioxidant. It believes, and antioxidants also, and compound, and fluoride, and sweetener, and tannin. Some of these, by the way, I think tea contains fluoride. But here's why NELL believes it. Tea plants accumulate fluoride. It found that phrase on the web. And tea is a natural source of fluoride. Okay, so I believe it. Tannin, caffeine, all kinds of things tea contains. It believes it's an agricultural product grown in certain states and provinces. It believes it's an agricultural product grown in certain kinds of landscape features. Believes it's a kind of crop and a kind of product. And my favorite, inverse of baked good served with beverage. It believes tea is a beverage that's served with biscuits, the baked good biscuits and bread and breads and breakfast and cakes and cookies and crackers and meats. Meats is not really a baked good, that's an error. Yeah, these are NELL's confidences, and many of them are overconfident. So one place we need help, maybe all can help, is giving NELL a better sense of what probabilities it should assign to these things. So it really does not do a very good job at that at the moment. The rankings are generally informative, but the absolute numbers are pretty terrible. Okay, so you get the idea. And for, why does it believe tea is served with pastries? Because, again, it has a number of phrases that it has used to do that. Okay, so there are a couple reasons I wanted to show you tea. One was just to introduce the basic idea that NELL reads by doing a rather shallow but high volume analysis of text. But the second reason I picked tea in particular is it turns out all of these relations that we were just looking at, like beverage served with baked good or agricultural product grown in certain kinds of landscape features, every one of those relations was one that NELL made up. It was not part of the initial ontology that we gave NELL. And it's something that along the way, over the last 2 years, it has decided is an interesting relation, and we'll talk more about what we mean by that. And that actually explains the weird naming convention here too a little bit. But these are all relations that it has added to the ontology, as well as facts that it has then gone on to read about instances of those. Okay, so that's enough for browsing the NELL website. Feel free to do that yourself, and if you do, you'll notice that when you go to the website, you can see recently extracted beliefs, and if you disagree with any of them, Which one? Which one are you laughing at? Rice. Lambs eat rice? You don't believe it? Okay, if you don't believe it, you can click the thumbs down thing and give some feedback. Okay, so come in, please come and browse, and please, if you do browse, give some feedback to NELL. It needs help. I'll just close out of that. Okay, so that's what is inside. Now let's talk about how NELL really works. And it's a kind of an intricate system, but the good news is there are, I think, 4 good ideas in NELL that explain the degree to which it works, and there are plenty of senses in which it does not work perfectly or even adequately. You saw some of those errors that were in the knowledge base as we were browsing. Meat is not a baked good. And the confidences, as you see, are pretty poorly assigned. And it has plenty of other shortcomings, some of which will come out in this talk. But let's look at, my goal for the next 30 minutes is to get across what are the 4 key ideas that make NELL work as well as it does. And I'll just point out, to motivate this, that we spent about 1.5 to 2 years trying to get this to work and floundering pretty miserably before we got together enough of the ideas to have the courage to turn the system on in January 2010. So there were a couple of years of just trying to figure out how you would assemble this thing at all. So key idea number 1 has to do with the core question of what NELL's learning task is. NELL's learning task includes, as we saw for T, learning to take noun phrases and classify them into categories like agricultural products, beverages, emotions, and hundreds of others. And also taking pairs of noun phrases like tea and foothills and deciding yes or no, does that pair of noun phrases satisfy any particular relation. So you can think of these as classification problems. And as you might recall, NELL has very little labeled data to go on. We gave it a dozen examples of each of those. So when we define beverage, we gave it a dozen beverages. There are 50 million unlabeled noun phrases it has, and probably a few hundred that it has that are labeled. So it's got to learn in a mostly semi-supervised way, but with mostly unlabeled data. Okay, so the key idea number 1 is, how do you design an algorithm that can do that can work with a small amount of labeled data? Suppose, for example, I want you to learn to recognize noun phrases that refer to cities. And I give you these 4 examples: Paris, Pittsburgh, Seattle. What kind of algorithm would you use? So maybe you would come up with the same thing we tried at first, which is, well, let's just build a kind of bootstrap thing where we'll take those 4 noun phrases that you told us were positive examples of your category. We'll find instances of those on the web, and we'll look at what kind of phrases occur around them. And we might find mayor of Montpellier and mayor of Pittsburgh live in Seattle. And so we'll find what phrases occur with those, and then we'll use those as extraction phrases to find more noun phrases that are found in those contexts. And sure enough, we'll find things like mayor of San Francisco, live in denial. And in fact, NELL did find this. And then we can take now these 4 original positive examples and these 3 inferred positive examples and find more phrases and iterate that process. And if we do, this is the kind of thing that will happen. It'll look kind of reasonable, especially in the early iterations. But the longer you go, what happens is there will be some, well, let's call them errors that creep in. And over time, they'll kind of blur out what used to be originally a very crisply bounded category. So you might say, that's not a very good algorithm. I wouldn't argue with that. But actually, I think more correctly, I would say that's not a very good problem formulation. Because the bottom line is that this is an under-constrained problem. If you think about what we're asking the program to do, you couldn't do it either. If I give you 4 words that you don't know, and I say, go ahead and learn to extract more that belong to this secret category that these 4 words belong to, it's a very under-constrained thing. I might have been thinking of northern hemisphere cities that begin with a consonant. Or I might have been thinking of the union of that with personality traits. This would be 4 examples of either of those categories as well as cities. So in that sense, it's really unfair to criticize the program. It came up with some set of things that includes those 4 and others. So in that sense, I think it's an unfair problem formulation, or whether it's fair or not, it's a failure-bound problem formulation. So good idea number 1 out of the 4 in NELL is don't even try to solve that problem. It's the wrong problem, it's way too hard. A much easier problem is don't try to learn a single function. Instead, try to learn many functions simultaneously in a way that those functions are coupled. And I'll say more exactly about what I mean by that. But this is key idea number 1 in NELL. NELL, instead of learning 1 function, is learning about 2,500 of these noun phrase labeling and noun phrase paralabeling functions in a multitask learning setting that couples them all. So in fact, we've identified 3 types of coupling that are useful. I'll go into this first one in a little detail just to make the point. So let's think of classifying noun phrases as person or not, referring to a person or not. So one way we could train a function is to represent each noun phrase by the phrases that it occurs with, kind of like we saw NELL doing when we browsed the knowledge base. And we could, for example, learn some linear logistic regression function, for example, that would assign, take any noun phrase like arm, or maybe arm, let's take blackboard. And we could take a noun phrase like blackboard and the noun phrase Oblinsky, and we could have a function try to decide which of those is a noun phrase based on, or is a person based on its frequency of occurring in these different contexts. And if we did, we would set that up as a supervised learning problem where we try to pick the weights on these different features in our weighted logistic function to minimize the number of mistakes the system makes over the labeled data. We'd say, okay, we're trying to minimize the predictions of our function about whether it's a person given a noun phrase, minus the difference between that and the actual label of whether it's a person over all the labeled data. Problem, of course, we don't have very much labeled data. And so one type of coupling, which is called co-training or multi-view learning, is instead of learning 1 function, let's learn 2 that use different features. that are uncorrelated. So in addition to learning this red function, we can learn a blue function that takes the same noun phrases, blackboard and Oblinsky, and instead of representing it in terms of context it occurs with, we'll represent it in terms of the morphology, the orthography of the noun phrase, the exact character string. And we'll have features like, well, is the noun phrase capitalized? Does it end with ski? Does it contain UNIV period? Different features of the noun phrase itself. And we can, again, make a different logistic function, the blue one. And now here's the key, the central idea. When we go to train this, remember what we're trying to do is we're trying to learn weights for all these features for the red function and weights for all these features for the blue function. But now look what happened. I changed, when I added that, I got to change the objective function that I'm optimizing when I pick my weights. Instead of just minimizing the number of mistakes the functions make over the labeled data, I also get to use now the unlabeled data. Why? Because for every noun phrase that I find, every one of those 50 million noun phrases on the web that I don't know whether they refer to a person or not, I do know that if function 1 and function 2 are going to be correct, they're going to have to agree. They can both say yes, it's a person. They can both say no, it's not a person. But if they disagree, then at least one of them is wrong. Exactly one of them. So this is the key. Think about what's happening here. How many labeled examples of person does NELL have? About a dozen. So these two terms in the objective are very small. How many unlabeled examples? About 50 million. This is an incredibly powerful constraint. The more unlabeled data you have, the better, the stronger this constraint. So that's what I mean when I say don't try to learn just one function, try to learn several in a way that's coupled. And in this case, here's the coupling. Okay, once you get that idea, it's easy to run with it. For example, NELL doesn't use just two views, it uses a third view too, which is the product of Richard Wang's PhD thesis, where every noun phrase also is characterized in terms of particular URL-specific HTML structures. So for example, if it's found as a list item on www.celebrities.com, then that's a feature of the noun phrase. You can imagine there are a lot of these features, but Richard's program has a smart way of just looking for potentially useful features like that and then learning a function from them. But the point is, each of these three features is a different view on the noun phrase, and the errors made by these red, blue, green functions are pretty much uncorrelated errors. And once you get into a situation where you have uncorrelated errors from these different views, you can get a great leverage from the unlabeled data. Okay, so that's the first type of coupling functions in NELL. In addition, a second type of coupling is instead of using different views of the same noun phrase to predict one label like person, NELL also has to learn to predict a lot of different labels. So this is the multitask learning part. NELL has to predict whether Oblinsky is a person, but also whether Oblinsky is a sport, and also whether Oblinsky is a team. And in the ontology, we define these categories in a hierarchy so that NELL knows an athlete is a kind of person. And so it knows that if the labeler for athlete says, yes, this noun phrase Oblinsky is an athlete, then that implies that Oblinsky is also a person. And so there's another kind of consistency constraint between the parameters of those two functions. And similarly, it knows if something's a person, then it's not a sport. And so that's another kind of mutually exclusive consistency constraint. Okay, so then we put these two together. For each of those labels, we have these three views, the context, the morphology, and the URL, HTML context. And so each of these black arrows now becomes a separate Boolean function that NELL is learning in this big coupled system. The final type of coupling actually comes from the fact that NELL also has to learn relations. Remember, it also is looking at pairs of noun phrases and deciding things like, does this pair satisfy the relation that noun phrase 1 plays the sport noun phrase 2? And when we define in the ontology these relations, they're typed relations, which means that NELL knows that if you, to satisfy the play-sport relation, you need an athlete and a sport. And so that gives us coupling between the parameters of the relation labelers and the individual category labelers for the arguments. Okay. So those are the three types of coupling functions. And taken together, that's actually, if you only get one idea out of this talk about what's going on in NELL, this is the single most important idea. Until we kind of figured that we had to go this way, nothing worked. And since we started going this way, things work a lot better. And furthermore, it scales just the way you want. The more functions you ask NELL to learn, and the more coupling you put between those functions, the better, more accurately it learns. And you can kind of see why, right? We started with that extreme example where there was just one function. And I think you agreed with me that that was an unfairly difficult problem. So every time we make this a more intricate graph of black arrow functions, the better constrained the learning problem becomes, and the better, more accurately things learn. Okay, so let me quickly show you what some of that other learned stuff looks like. We already saw a number of these extraction patterns that get learned. What about those morphological features? What does that look like? Well, that looks like this. For example, the classification of noun phrases looking just at the character string of the noun phrase, that learns features like this. And it's a logistic regression function. And for example, to decide whether a noun phrase refers to a mountain or not, NELL has learned that if it's a multi-word noun phrase like Pike's Peak, then the fact that the last word is peak is a very positive weight indicating probably this is a mountain, Pike's Peak. Or if the last word is mountain, that's also a very positive indicator. If the first word is mountain, it's actually a negative indicator. Mountain bike, mountain goat. Those are not mountains. Similarly, you know, for other categories, if it's a newspaper, if the last word is sun, that's a good indicator. Visual art movements, if they end with ism, that's a good indicator. Impressionism, but not if they begin with Buddhism. That's negative. Then it's not a visual art movement. Buddhism is not. So this kind of morphology information gets learned is complementary to this. Taken together, we get very independent kinds of errors between the two. Here's the third kind, those URL-specific things that are learned by Richard Wang and William Cohen, his thesis advisor, their system. And I'll just read you one of these. This says, if you're looking for the relation book author, then you should go to lifebehindthecurve.com and look for HTML structure that essentially is a list item with X by Y. Then you should assume that X is a book written by Y. So these are very targeted, specific URL HTML indicators. And again, they're imperfect, but they make errors that are pretty much independent of the other views. Yeah? Yeah, these are all learned. This whole thing is learned. And I should say, so there are millions of features that are being considered in this morphology one, basically substrings up to some length. And these URL-specific features are basically grown outward by searching for web pages that contain purported things that the knowledge base believes are book author pairs, finding web pages that mention multiple believed book author pairs, and then just learning the patterns that surround those. So it's not a fixed list of these, they're just kind of synthesized out of that. Okay, so you get the idea, and this leads to a very simple architecture, software architecture. NELL is essentially an infinite loop, which you can think of as an EM, expectation maximization style learning method, where on every time through the loop, each of these different learners that we just looked at, and humans, if they give any advice, get to suggest things for the knowledge base. There's something that integrates the suggestions from these different sources and adds them as official beliefs to the knowledge base. And if you think in terms of EM, that's the E step. The knowledge base is, you could think of as a whole bunch of latent, unlabeled beliefs, true or false, and on every iteration, essentially, these learning reading components get to suggest beliefs. And then on the other half, the M step, that current knowledge base is used to retrain all of those learners. And so in that sense, it's a very simple, infinite EM style loop. There's some subtleties to how you do that at this scale, and mostly it's by cutting corners and not really labeling every one of the 50 million noun phrases, just the ones that the system is most confident in at the moment. And then as it progresses, its confidence, there are more and more noun phrases in which it becomes sufficiently confident to make a prediction. Okay, so that's the idea. And that's idea number one. If you're going to do semi-supervised learning, make it easy on yourself by learning thousands of functions that are coupled instead of trying to learn just one, which gives you an insufficiently constrained learning task. Okay, good idea number two comes out of that. If coupled learning is key idea number one, then how can we get even tighter coupling, more coupling constraints? And the idea in key idea number two is we learn them. Now that NELL has a knowledge base with millions of beliefs, it can data mine those beliefs. They're not all correct, but they're correct enough that empirical regularities show through. So NELL mines that database to learn probabilistic horn clauses like this one that says, in English you would read this, if athlete X plays for team Z and team Z plays sport Y, then athlete X plays sport Y with probability 0.93. And so this is just an empirical regularity that can be discovered from the millions of facts NELL currently believes using a FOIL-like learning algorithm. And so NELL now actually has thousands of these kinds of rules which it learns and then uses to infer new beliefs which it has not yet read, but which are inferable from these regularities. And here you see kind of a sample of some of them with different confidences. Okay, so that's key idea number two. You can data mine the existing knowledge base, and that gives us a fourth way, a non-reading way of inferring new beliefs. But it also corresponds to adding even more coupling constraints to our system of learning problems. And what do I mean by that? Well, think about it. That rule up there in the blue box is really a logical constraint among these three relations, right? And so it's adding a new coupling constraint that didn't previously exist about the joint assignments that are legal and illegal. If you're given three noun phrases, then X, Y, and Z, then your joint assignment of yes or no values for these three relations have to obey this logical constraint. So every one of these new learned inference rules is also effectively a new coupling constraint used in order to further improve the constraints for learning to better read those things. So now we have this kind of positive cycle, right, where notice two things here. Number one, NELL couldn't really learn these rules the first 6 months it was running because it didn't know enough. Didn't have a big enough knowledge base to have a statistically